So now that we have a visual and intuitive understanding of what correlation between two variables actually represents, let's try and quantify this. Let's try and find a number that really indicates that the correlation between these two variables is much lower than the correlation between these two variables. And as always, it's not getting this number that is the hard part. This can be done in just a few lines of Python code. What is the hard part is building up the understanding of what it actually represents. For instance, the p-value and now correlation, which we did throughout this course already. Now remember that for linear correlation, and thus for computing a measure for linear correlation, we assume that our two datasets, x and y, are normally distributed. Now, if this is indeed the case, we can compute the Pearson Correlation Coefficient. And in Python, this can be done very easily with just one line of code, stats.pearsonr, and then our two variables or our two datasets. Now this function returns the correlation coefficient, or called r. Now this is a number between -1, which indicates a perfect negative correlation, and +1, which indicates a perfect positive correlation. Now what most people forget is that this function also returns a p-value, and this is incredibly important in addition to just this Pearson R number. And this p-value represents the likelihood of getting the specific correlation number r that we got for our two datasets under the null hypothesis. And the null hypothesis in this case is that the two datasets are not correlated at all. Or yet in other words, what is the probability that you got your specific correlation coefficient just out of pure coincidence? Now this p-value is incredibly important to always include in your data analysis, because it allows you to also mention your confidence in your conclusion. So armed with the Pearson Correlation Coefficient, or this R number, and the corresponding p-value, we can now go through our plots again, but now each time also showing the Pearson R and the p-value. Now in this first figure, we see of course that there is perfect correlation. All of these points lie on a perfect line, and this represents itself in a Pearson R coefficient of 1 and a p-value of 0. Now again, this p-value of 0 represents that there is absolutely zero chance that you would have gotten exactly these data points out of sheer coincidence. So you can be very confident in your correlation coefficient of 1. Now if we increase the noise, then we see that this Pearson R coefficient actually decreases. However, the p-value still remains 0, because also in this case, to get data points that lie roughly on a line just by coincidence is basically 0. So if we increase our noise even further, then we will see our Pearson Correlation Coefficient decrease. But still, our p-value is 0.0. So even in this case, if our x and y would be perfectly uncorrelated, then getting these data points in this way, which is still roughly on a line, would be incredibly unlikely. And this is represented by the p-value of 0. Now we can decrease the correlation even further if we change this a parameter. Remember, this a parameter is this number that we multiply with to get a y value for each x value. So if this a parameter goes closer and closer to 0, then we in effect diminish this connection between x and y. So let's take a look and see how it also influences our Pearson R coefficient and the p-value. So in this case, if a is 0.2, we see that our points are more and more looking like a random blob. And indeed, our Pearson R coefficient is now only 0.36. But even in this scenario, where it becomes quite difficult to see visually from our scatter plot that x and y are correlated, our p-value is still 0, which means that this specific scatter plot is still very unlikely to have been emergent from two datasets x and y that are completely uncorrelated. So still here, we can be very confident in saying that x and y are indeed correlated. But what happens if we now go to the extreme scenario, where a is equal to 0? Now remember, this is the case where x and y are completely uncoupled from each other, and therefore we expect there to be 0 correlation. Now still, the Pearson R coefficient is not exactly 0, it's 0.07. However, Then we look at the p-value and we see a p-value of 0.22. This means that there is a large enough chance to get this specific R value of 0.07 from two datasets that are completely uncorrelated. Now, because this p-value is not less than our statistical significance of 0.05, we cannot confidently conclude that the correlation that we found here, which is still very small, is indeed significant. And thus, from this scenario, we must conclude that X and Y are uncorrelated, which is of course in theory true because we set A equal to 0. So even though we found an R value that is not 0, the p-value saves the day and forces us to conclude that X and Y are not correlated. Now, before we dive into the code and look at the actual Python lines that compute this p-value and the Pearson Correlation Coefficient, let's look at some alternatives. Now, why alternatives? Because, as I mentioned before, there are some requirements on X and Y such that the Pearson Correlation Coefficient is valid. Namely, the connection between X and Y must be approximately linear, and both of our X and Y had to be normally distributed. But what, of course, if this is not the case? What if one of these two is just not fulfilled? Well, let's first look at the case where X and Y are not normally distributed and not linear. So both of these conditions are not met, but we still have the condition of a monotonic relationship between X and Y. Now, what does this mean? Monotonic relationship means that the relation between X and Y, if we plot them on a scatter plot as before, is either always increasing or always decreasing. However, in this case, this increase or decrease doesn't have to be along a single line. It can also, for instance, be on a curved line, as long as it's always in or decreasing. Now, in this case, to compute a measure for the correlation between these two variables, we use the Spearman R coefficient. And this is also computed in one line of code, stats.spearman R, X and Y. Now, as was the case for the Pearson Correlation Coefficient, this function also returns, on the one hand, a number R, which is a measure for the correlation, which goes between -1 and +1, and also a p-value, which gives you a confidence of finding this specific R value under the null hypothesis that the two datasets are uncorrelated. But what now if also this monotonic condition is not met? Well, then there is still one function that comes to the rescue, namely the Kendall-Tau coefficient. This is again a measure for correlation between two variables, but these two variables don't need to come from normal distributions, and they also don't need to be linear, and their relation also does not need to be monotonic. And we will see an example of it right away. But also here, we can compute this coefficient with stats.Kendall-Tau and then X and Y, which again returns a coefficient between -1 and +1, but also a corresponding p-value. Now let's look at two examples, one scenario for each of these two coefficients. In the first one, we see that clearly the relation between X and Y is not linear, because these points, even though they seem to be very correlated, do not lie on a straight line, but more or less on this curved line upwards. However, we do see that this relation is monotonic, namely, it always increases. At no point does it go down again. And this is a perfect scenario for the Spearman R coefficient. And again, if we compute the Spearman R coefficient, we see 0.93. So very correlated, because very close to 1, and the p-value is 0. So we can be very confident. Now also from this visualization, we see that even though X is normally distributed, Y is certainly not normally distributed. So that's also a reason why we couldn't use the Pearson Correlation Coefficient. So let's now look at the last example where indeed none of these conditions are fulfilled. Now we immediately see that these points do not lie on a line, so there is no linear connection between X and Y. But also, the connection between X and Y is not monotonic. We can see this because in this part of the graph, X and Y increase together, because if X increases, Y increases. However, if we pass X is equal to 0, we see that while X still increases, Y actually decreases. so there is no monotonic relation between these two variables. Now, to still get a measure of correlation, because we indeed see from this scatter plot that these two datasets are indeed quite correlated, we have to use the Kendall-Tau correlation coefficient. In this case, it's 0.92, which is again very close to 1, so indicating that there is a very tight connection between x and y, and the p-value is equal to 0. And therefore, we can be very confident that this number that we got for our correlation is not just due to pure chance. Now, to end off this lesson, let's dive into the code and see how we can compute these coefficients ourselves, but also how we can generate these weird data sets. So let's go to the code. And we again see the same code cell as in the previous lesson, because we will be able to use a lot of what we had before. In these lines, we generate our two data sets. But now we can also address these two commented lines, which generate a different data set. Here we just had y is equal to a times x plus our noise to make it less correlated. But now we also have y is equal to a times the exponent of x. And this gives us a non-linear but still monotonic relation between x and y. And we also add our random noise, of course. And then in the third line, we have y is equal to a multiplied by the cosine of x to get this non-linear but also non-monotonic scatter plot between x and y. And also here we add some random noise. So later in this lesson, we will uncomment them and see what this gives. But at this point, we scroll down and skip all of the plotting parts, and we go to the part where we actually compute these coefficients. And as always, getting these numbers is very straightforward using Python. So we define the Pearson R coefficient with the corresponding p-value, and we obtain these values by just doing stats.pearsonr, our x dataset and our y dataset. And this gives us our two numbers. And of course, we can then print them out using fprint statements. Now, exactly the same can be done for the Spearman R coefficient and its corresponding p-value, and the Kendall-Tau coefficient and its corresponding p-value. Now, if we run this cell, and remember in this case we had a linear correlation, which was this one, but it wasn't that tight. And so if we scroll down to our print statements, then we see the following. So our Pearson Correlation Coefficient is 0.71. So it is very large, but it's not obviously large. And the p-value is 0.0, so the chance that we've gotten this specific correlation coefficient for our datasets in the case that our datasets were uncorrelated is basically 0. So we can be very confident that indeed our datasets are correlated to each other. Now we can of course also compute the Spearman's correlation coefficient and the Kendall's Tau coefficient, even though they are less strict than the Pearson correlation coefficient. So if we run this cell again and again, then we will see again that we're working with statistics and generating random numbers, because each time these specific values will fluctuate a bit. But we will see that they always are roughly the same. Now this is still a very obvious case of correlation. So let's change our parameters and make the correlation much more difficult to spot visually. So let's say that we take a is equal to 0.2. Now if we scroll down, we see that the correlation between x and y visually is not that clear. Well, at least for me, I wouldn't really want to make any conclusion starting from this scatter plot. So if we go down then we can still see that the Pearson correlation coefficient is not 0, so indicating a correlation of 0.18, and the p-value in fact is very small. So even though we couldn't really derive correlation between x and y by looking from this scatter plot, the Pearson correlation coefficient in combination with the p-value allows us to make a confident conclusion that x and y in this case are indeed correlated to each other. Now, of course, if we run this cell again, then we see that we each time get a different value for our correlation coefficient. But each time the p-value will be low enough to be very confident in this correlation. So let's now scroll up and remove our linear relation between x and y. So if we comment this line, well, first of all, we set a is equal to 1 again, and then we uncomment this line. Now in this case, y is generated by first putting x in the exponent and then multiplying it with a number, and of course adding noise. So in this case, x and y are clearly not linearly related to each other. And thus, in this case, we have to use the Spearman's rank correlation coefficient. In this case, it gives 0.7 with a p-value of 0.0. So we are very confident in that these two datasets are indeed related to each other. And then to end off, we can uncomment the last way of generating y, which is in this case a non-monotonic, non-linear relationship between x and y. So if we scroll down, then we see this one. And in this case, we see that our correlation coefficient, the Kendall's tau coefficient, is minus 0.048. Very, very small. And indeed, if we look at the p-value, then this is larger than 0.05. And this means that this specific value for the measure of correlation for our datasets could have been easily obtained if our two datasets were uncorrelated to each other. So if we run this cell again and again, then we see that it is very difficult to determine the correlation between these two datasets, because each time this p-value is just too large to allow us to make a confident conclusion. So let me now just scroll up and put everything as it was before. So we have a linear relation between x and y, and a and the noise parameter are very normal values. Now also for this Jupyter notebook, I highly recommend that you go back and change these parameters around. And each time you change a parameter, try to figure out first how you expect the scatter plot and the correlation coefficients to change, and then check your result. And in this way, you can build up a very sound and deep and intuitive understanding of the correlation between two continuous variables. And this brings us to the end of the first part of our chapter on correlation, where we looked at the correlation between two continuous variables. Now the go-to measure for this is the Pearson Correlation Coefficient. However, this one is only valid if two conditions on the underlying datasets are fulfilled. If these conditions are not fulfilled, then there are two alternatives. But remember that even though these two alternatives are available, they are much weaker, meaning that the confidence in your conclusions will be much less than in the case for the Pearson Correlation Coefficient. Now it's important to stress here that what we did is we identified the correlation between two variables. If you want to go a step further and use this connection between these two variables to actually make predictions, well, then you are in the material of the bonus chapter, where we will look at linear regression, which does exactly that. Now in the next lesson, we will start with part 2 on correlation, namely identifying and quantifying correlation between two categorical values. So I will see you in the next lesson.